the last video we looked at Newton's second law, and Newton's second law was F equals ma. And what Newton's second law told us was that if you apply a force to something, so here I'm applying a force to an object, that object will tend to accelerate in the same direction as that force. And obviously, if that force gets bigger and bigger and bigger and bigger, so if you apply a bigger force, the acceleration will get bigger and bigger and bigger and bigger. So what we said was the amount that something accelerates by is proportional to the force applied to it. And that makes sense. If you have an object on your table there, like a book, and you push it with a small force, it will accelerate with a small amount. If you push it with a much larger force, it will accelerate more. So today we're going to look at a couple of ordinary level questions, and this one we're going to look at today is the 2009 ordinary level question 4a, where we use Newton's law. And in all of these questions you use Newton's law. So let's look at it. We have two particles of masses 3 kg, here's the 3 kg and 2 kg, and they're connected by a taut, light, inextensible string. Now the fact that it says light there means we don't worry about the mass of the string. Basically we assume the string has no mass. And the fact that it's taut means that it's always tight, so the force is always constant, really, is what this is telling us. And that will make sense when we look at the question, what I mean by the force being constant. So basically we have this set up here. The system is released from rest, so originally nothing's moving. And part 1, show on separate diagrams the forces acting on each particle. So first of all, let's just look at what we think is going to happen here. Well, we'd assume that when you release this from rest, the 2 kg particle is going to move down and the 3 kg particle is going to move to the right. If it goes from rest to moving, it accelerates. So this is going to have a certain rate of acceleration. Let's call its rate of acceleration A. Now because that string is taut, because it's tight, the 3 kg mass is going to move to the right at exactly the same rate as the 2 kg mass is going to move down. So therefore we can call this A as well. They'll both have the same acceleration. So that's what we assume is going to happen. Let's look at part 1. Show on separate diagrams the forces acting on each particle. In ordinary level they always ask you to do this. In higher level they don't, but the first thing you always do is force diagrams. And you'll see why that is important as we go through the question. So let's look at the 2 kg mass. Here's the 2 kg mass. What forces are acting on the 2 kg mass? Well, gravity is pulling it down. It's weight. And weight, remember, or you might remember from junior cert, is equal to something's mass multiplied by gravity. So in this case it has a mass of 2 and gravity is g, 9.8. So the downwards force, we would say, is 2g newtons. That's the force that's pulling it down. Is there anything stopping it being pulled down? Well, because it's attached by this string to the 3 kg mass, that's going to kind of slow it down. That's going to pull it up. And usually if there's a string involved, we call the force T for tension. So that would be the forces that are acting on it. Gravity, or its weight, is pulling it down. And what's stopping it from moving down quickly? Well, tension in the string. So that's the force diagram for the first one. Let's look at the force diagram for the second one. The 3 kg mass. For the 3 kg mass, well, what's it being pulled by? Well, it's being pulled to the right by the string. And because this is the same string attached to the 2 kg mass, the force will be the same. So there's tension pulling it to the right. Is there anything pulling it back to the left? No, there's not. Now, if there was friction, there would be something that's slowing it down. Friction would slow it down. But in the question, it said that the table was smooth. And anytime you see the word smooth in the question, it means there's no friction. But as we move on to the harder questions, you're not going to see the word smooth, you're going to see the word rough. And rough means there is friction. But for today's questions, there's going to be no friction in any of them. Okay? So that's the forces acting on it in that direction. You could also add in its weight, which would be 3 times g. And because it's not falling through the table, as if you have any object on a table, the table is pushing back up in it, and we call that force the reaction force. If the reaction force wasn't there, any object you put in a table would just fall through the table. but in this case it's not moving up or down, so therefore the reaction force equals 3G. Now we don't need that for today's question, but we will look at that in more detail later on. So that's part 1 done. There are all the forces acting on each particle. Part 2, find the common acceleration of the particles. In other words, they want us to find A. Now here's where Newton's second law comes in. Okay, for each particle, and I'll go over here. For each particle, we use our F equals ma equation. Now first of all, we need to look at what way they're accelerating. So this particle, we said, is going to accelerate downwards with A. So what's the force on this particle? Well, the force on this particle will be, in the downwards direction, will be 2G. But that's not the overall force in it. Remember last lesson we talked about resultant force. The resultant force will be 2G minus T, because the tension is pulling it back. So if I wanted the overall force in it, it would be 2G minus T. In exactly the same way, if I had a block that was being pulled down with a force of 5 newtons and being pulled up with a force of 2 newtons, what's the overall or resultant force in it? Well, it'd be 5 minus 2, it's 3 newtons. Overall, the force is 3 newtons downwards. And that's all we're doing here, we're just doing it using an expression. Equals its mass, which is 2 times A. So we write out that equation, 2G minus T equals 2A. And we're going to call that equation 1. Now if you look at this, we've two unknowns. We don't know what T is and we don't know what A is, but G actually isn't an unknown because we know G is equal to 9.8. So you do that for the first object and then you do exactly the same thing for the second object. I'll do it in a different color pen. But again, we look at the direction that it's accelerating in, and this object is going to accelerate to the right. So when we do F equals ma, we're only looking at forces which are in this direction, horizontal, because that's the direction it's accelerating in. So we don't need to worry about 3G or the reaction force, we just look at T. And because T is the only force, T is our force, equals its mass, which is 3 times A. And that's equation 2. Now we have two equations. I'll write them out again here. Equation 1 was 2G minus T equals 2A. And equation 2 was T equals 3A. So we just need to solve these two equations to find A. You could do simultaneous equations or you could do substitution. And substitution looks like the best option here. So I'm going to substitute this T with 3A. And equation 1 will become 2G minus 3A, because T is the same as 3A, so I can put in 3A here, equals 2A, plus 3A to both sides, and we get 5A equals 2G. Divide both sides by 5. Remember the question was to find A. They cancel, so A equals 2G over 5, and you can leave your answer like that. You can put it into a calculator, but usually your answer is more accurate if you just leave it as a fraction. So our unit of acceleration, remember, is meters per second squared. And that's your answer to part 1. Part 2, find the tension in the string. So we know what A is. We know A is that. And to find the tension, this is easy because tension is equal to 3 multiplied by A. So tension is going to be 3 multiplied by 2G over 5, which is 6G over 5. And the unit of tension is newtons, because it's a force. So we remember a unit of force is always newtons. So there's your answer for part 3. So that's the question done. I'll do another example in the next video and then I'll give you a couple to practice.